Alright, in this video we'll be going through the 2021 Level 3 Mechanics Exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you've completed the question or get stuck, unpause the video and see how I go about getting the answer. Okay, question 1. A simple balancing toy can be made by joining two masses with a rigid wire. The distance between the center of mass of the angler and the fish is 14 centimeters. The pivot point is at the bottom of the pole under the angler and is 5 centimeters below the center of mass of the angler. Assuming the wire has no mass, show that the center of mass of the system is 3.75 centimeters below the pivot point, along the line joining the angler and the fish. Okay, so we know that the equation for our center of mass is x center of mass is equal to m1 x1 plus m2 x2 all over m1 plus m2. Now we can set the center of mass of the angler as our reference point, and therefore this is going to be our x1, and as this is our reference point, x1 is equal to 0, okay? And so now plugging in our numbers, our m1 is 30 grams, times our x1, which was 0, remember, plus our m2, which is 50 grams, times our x2, which is 14 centimeters, all over 30 plus 50. And this gives a center of mass of 8.75 centimeters. Now remember, this is 8.75 centimeters from the center of mass of the angler. So this right here, this distance, is 8.75 centimeters. However, we want to find the distance below the pivot point, okay? So we want to find this distance right here. That's the distance we're trying to find. So we can see that this distance, which we can call x, is equal to 8.75 minus 5, right? This 5 right here. And so our x is equal to 3.75. And as you can see, that is the value that we're trying to find. When the toy is rotated about the pivot, a torque due to gravity acts on the toy. Show that when the toy is rotated by 42 degrees, as shown, the torque about the pivot is 0.0197 Newton meters. So, first off, we can see right here that this toy is going to have a weight force acting straight down. And remember, everything acts from the center of mass. So this is the center of mass right here. Now we can break this weight force down into components, as so, okay? Where this angle right here is 42 degrees, okay? This is our weight force, and so therefore this is our weight force sine 42 degrees. This is our weight force cos 42 degrees, okay? Now remember, when we're talking about torque, we are looking for the force that is perpendicular to the radius of rotation, okay? And so as we can see here, this component of our weight force is the component that is perpendicular, okay? It's going to look something like this, okay? So we're looking for this component right here, because that is the one that is at right angles and therefore perpendicular to the axis of rotation, okay? And so, therefore, as we know, our torque is our force times our distance, where in this case, our force is our Fw sine 42 degrees, and our distance is the distance from the pivot to the center of mass, so it's this distance right here, and as you can see, that is our x value, and in the previous question we found our x value as 3.75 centimeters, and therefore 3.75 centimeters is 3.75 times 10 to the negative 2 meters, okay? And we obviously know our weight force is equal to mg, right? So we can make that substitution right here. And therefore our torque is equal to our mass. Now in this case, as the rod that connects the two masses together, this rod right here is weightless. The entire mass of the system is the mass of the angler, which is 30 grams, and the mass of the fish, which is 50 grams. So therefore, that would be 30 plus 50 grams. And so therefore, that's times 10 to the negative 3 to convert it into kgs, right? Times 9.81 times sine 42 degrees times 3.75 times 10 to the negative 2 meters, okay? And so therefore this gives a torque of 0.0197 Newton meters. There we go, and as you can see, that's the value that we're trying to find. The rotational inertia of the whole toy is the sum of the rotational inertia of each mass. The rotational inertia I of each mass can be estimated by treating each as a point mass, for which I is equal to mr squared, where m is the mass of the object and r is the distance from the pivot. Use the information given to estimate the rotational inertia of the toy about its pivot point, and hence the angular acceleration when released from the position shown in part 1. So therefore the total rotational inertia is equal to the rotational inertia of the angler plus the rotational inertia of the fish. So now plugging in our numbers, the mass of the angler is 30 grams, and we need to convert that to kg, so therefore it's times 10 to the negative 3, times our R value, which again is the distance from the pivot. And as we can see, the angler is 5 centimeters away from the pivot, okay? So 5 centimeters is 5 times 10 to the negative 2 meters, and that's all squared, okay? Plus the mass of the fish, which is 50 grams, so therefore times 10 to the negative 3 again to convert to kgs, times the distance to the pivot, which we can see here is 14 minus 5, and therefore that's 9 centimeters, okay? So 9 times 10 to the negative 2, and that's all squared again. And this gives a total rotational inertia of 4.8 times 10 to the negative 4 kg meters squared. So that's our rotational inertia, but we are asked to find the angular acceleration. We know that torque is equal to I alpha, and therefore alpha is equal to torque all over our rotational inertia. We found the torque in the previous question, and that was 0.0197 all over our rotational inertia, which we just found, which is 4.8 times 10 to the negative 4. And this gives an angular acceleration of 41.04 radians per second per second. There we go. When the toy is released, it oscillates, but eventually ends up stationary in the rest position shown below. Discuss the energy transfers that occurs while the toy is oscillating, and explain why it always stops in that exact position. Alright, so if we take this height as equal to 0 right here, this height right here, and that is, again, h is equal to 0, we can see that as the toy comes up, it has gained some distance we can call delta h, okay? And we know when we gain some distance, as our EP is equal to mg delta h, we therefore gain some EP. And we can imagine when the toy is at its max height, it's going to be at rest momentarily. And so when it's at rest momentarily, that means its velocity is equal to 0. And so therefore its EK is equal to half mv squared. If our velocity is 0, our EK is also going to be 0. So when it's at its max height, its EP is going to be max, but its EK is going to be at its minimum. However, when it comes down, we can see it's going to end up right here, and that is where our h is equal to 0, and therefore our EP is going to be equal to 0. However, as it's coming down, that's when it's going to have its max velocity, and therefore its EK, in this case, is going to be max. So basically, as the toy oscillates, it transfers its energy from gravitational potential energy into kinetic, and then back to gravitational, and then back to kinetic, and it keeps going. The reason why it eventually stops is because this energy transfer process is not perfect, and we lose energy to things such as friction, okay, to the environment. So that's why it eventually comes to rest. Now, the reason why it rests in this position, we can see that in this question, we are at max displacement right here, and we have a net force acting downwards that is pulling us towards the equilibrium position. That is our restoring force, okay? We can see that when we are at our equilibrium position or our rest position, there is no restoring force, and therefore our torque is going to be equal to 0. And so therefore, as our torque is equal to I alpha, if our torque is 0, then our angular acceleration is also going to be 0. The Deep Space Climate Observatory satellite, a magazine article states that L1 is the point where the gravitational force of the Sun and Earth are balanced. Explain why this cannot be true if the satellite is moving in a stable orbit. Okay, so it says up here that the satellite is in a stable orbit around the Sun with the same period as Earth, okay? So this satellite is not orbiting Earth, it's orbiting the Sun. And so if we are in orbit, let's say we have our Sun right here, so S, and we have our satellite over here, and it's going in circular motion, we know that in circular motion there must be a centripetal force accelerating us towards the center of the circle, okay? And in this case, the center of the circle is the Sun, okay? So this is our FC. In this case, our FC is our gravitational force, okay? And remember, by definition, our FC is a net force, it's not a force in and of itself. And so therefore, as there is an FC, the forces can't be balanced, because if the forces were balanced, then there will be no net force, and so therefore no FC. Also, you could say that if we have our Earth here, our Sun all the way over here, much bigger, and we have our satellite over here, if the gravitational forces between the Earth and the satellite and the Sun and the satellite were equal, and we are moving in supposed circular motion, we would have a tangential velocity coming out this way, okay? And if these forces balanced out, there would be no FC accelerating us towards the center of the Sun, okay? Accelerating the satellite towards the center of the Sun. And so if there is no FC accelerating us towards the center of the Sun, there would be nothing to pull us into a circular path, and so therefore the satellite will just move off into this direction and then out of orbit into deep space. Okay? And so by definition, as the satellite is orbiting the sun, the forces between the satellite and the Earth and the satellite and the sun can't be balanced. Okay? There has to be a net force. The satellite, due to its L1 position between Earth and the sun, is under the influence of the gravitational field of the sun as well as the Earth. Show that the net gravitational field strength, G, at position L1 on the satellite, if it is moving in a circular orbit and is consistent with it having a period of an Earth year, is 5.88 times 10 to the negative 3 Newton per kg. Now, Newton per kg, if you don't know what that is, okay, so Newton per kg, that is the same thing as saying meters per second per second. So this is another way in which we can write acceleration, okay? How we know this is we know that force is equal to mass times acceleration, and we know the unit for force is Newton, we know the unit for mass is kg, and we know the unit for acceleration is meters per second, okay? And so therefore, plugging this into here, we get kg, meters per second, all over kg is equal to meters per second. And so we can cancel out our kgs, and what do you know? We have meters per second is equal to meters per second. Okay, so just another way to write acceleration. All right, so now that we got that out the way, there are two ways of solving this problem. The first one being we can take our FG value of the sun and minus the FG value of the Earth, and we'll get our net FG, right? And so what that would look like is our FG net is equal to the gravitational constant times the mass of the sun all over rs squared, where rs squared is this distance right here, okay? So this is rs, okay? And this we can call re, so r Earth, okay? And we can minus FGE, which will be the gravitational constant, times the mass of the Earth, mass of the Earth, there we go, all over re squared, okay? So we can take g out as a common factor, and we get g is equal to ms all over rs squared minus me all over re squared, okay? Now plugging in our numbers, we get our gravitational constant is 6.67 times 10 to the negative 11 times the mass of the sun, which is 1.99 times 10 to the 30, all over rs squared, which is 14.81 times 10 to the 10, and that's all squared, minus the mass of the Earth, which is 5.97 times 10 to the 24, all over re squared, which is 0.15 times 10 to the 10 squared, okay? And this gives an FG net of 5.87 times 10 to the negative 3 meters per second, okay? Now, by the way, the reason why when we use this equation right here, we get meters per second. However, when we use this equation, we get newtons as the unit. It's because of this extra mass right here. You notice we only use one mass for this, but there are two masses here, okay? If we use some dimensional analysis, we know that G has unit Newton, meters squared, kg to the negative 2, okay? And that's times by our mass, okay, which is kg, all over meters squared. And if we simplify this, these cancel out, and this power cancel out with this, and we get Newton per kg, and as we established over there, that is the same as meters per second, okay? However, if we take this equation, right, we have the same gravitational constant times kg, all over meters squared. We notice that these kgs will cancel out, this will cancel out with this, and we're just left with newtons, okay? And so that's how we get meters per second here rather than newtons. That might have tripped some people up, okay? So the second method that we can use is we can find the velocity of the satellite, and we know the velocity in circular motion is 2 pi r all over t, okay? If you don't know where this comes from, just remember that our velocity is distance over time, and if we have our circular motion, and if we have our satellite here, in one period the satellite covers this distance, and that is the circumference of a circle. Circumference of a circle is equal to 2 pi r, okay? And the time it will take the satellite to cover this distance is one period. And so our t value will be our period, and so that's how we get this equation right here, okay? And so our velocity is equal to 2 pi r over t. 2 pi times our radius, which we established up here as 14.81 times 10 to the 10, all over our t value, which we established is the period of the Earth, okay? So that's 3.1536 times 10 to the 7, and that gives a velocity of 29,507 meters per second, okay? And we know in circular motion, our acceleration is v squared over r. In this case, our acceleration is going to be g, and so that's v squared over r. And we just found our v, which is 29,507, and that's all squared all over our radius, which is the same value as over here. So we get 14.81 times 10 to the 10. And this gives us an acceleration of 5.88 times 10 to the negative 3 meters per second, okay? Now, as you can see, each value is slightly off, but if you actually think about it, this is times 10 to the negative 3, and this is our second decimal place, so that is a very, very, very small discrepancy, so it doesn't really matter. The satellite has special cameras pointing at the sun and at the Earth, so it has to spin with the period of one Earth year to keep in line with these objects as it orbits the sun. The solar panels on the satellite could be moved closer or further from the satellite to adjust the spin period. Explain how moving the solar panels further from the satellite would affect its angular velocity. So this is a classic question. We know our rotational inertia is directly proportional to mr squared, okay? Obviously, the mass of the satellite is not going to change, so we don't even have to consider that. However, when the solar panels extend, the effective radius of the satellite is going to increase. Now again, if you don't understand what effective radius means, watch my rotational motion video in my mechanics playlist. I go through it in that video, okay? So the effective radius is going to increase, okay? And therefore the rotational inertia of the satellite must also increase. As we know, angular momentum is going to be conserved, and therefore as angular momentum is equal to I omega, right? Where omega is our angular velocity, obviously. If our angular momentum remains constant, but our rotational inertia increases, therefore our angular velocity must decrease. And obviously the opposite is true, as I is directly proportional to mr squared. If the satellite were to bring its solar panels back in, its effective radius will decrease, and therefore its rotational inertia will decrease, again, as angular momentum is conserved, and angular momentum is equal to I omega. If I decreases, then its omega must increase, and therefore the angular velocity will increase, right? So there we go, you can put that in words. A small fragment of an icy comet hits the spacecraft and sticks to one of the solar panels at a distance 1.42 meters from the axis of rotation. The fragment has a mass of 0.78 kgs, and it increases the angular velocity of the satellite by 0.0124 radians per second. The satellite with the fragment is estimated to have a rotational inertia of 1.79 kg meters squared. Determine the impact speed of the fragment relative to the satellite. So we can figure out the change in angular momentum, by taking the rotational inertia and multiplying that by the change in angular velocity. We can see here that the angular velocity increases by 0.0124, okay, and we are given the rotational inertia. And so therefore 179 times 0.0124, and that gives us a change in angular momentum as 2.2196 kg meters squared per second. Now, this change in angular momentum came from the fragment, and so we can say that the initial angular momentum of the fragment is equal to 2.2196 kg meters squared per second, okay? As we know, angular momentum is equal to mvr, okay? We know the mass of the fragment and how far it is away from the axis of rotation, and so therefore we can find our velocity. And so our velocity is equal to L over mr. Therefore, plugging in our numbers, we get 2.2196 all over 0.780 times our radius, which is 1.42, okay? And this gives a velocity of 2 meters per second. There we go. A simple car suspension system rests with the weight of the car on 4 springs, each attached to a wheel. The mass of the car is 893 kgs. John sits on the roof in the middle of the car and then slides off carefully to quickly release his weight from the car, without pushing down on it. He watches the car oscillate up and down. It completes one oscillation in 1.14 seconds. Show that the spring constant for the combined 4-spring system is 2.71 times 10 to the 4 newtons per meter. We know that our period is equal to 2 pi square root m all over k. We know our period as it's given right here. We know the mass of the car as it's given right here. And we are trying to find the spring constant, and obviously pi does not change, okay? And so we can rearrange for our spring constant, and we get t divided by 2 pi is equal to square root m all over k. T over 2 pi squared is equal to m over k. And therefore k is equal to m divided by t all over 2 pi squared. Okay? Plugging in our numbers, we get our spring constant is equal to 893, I believe. Yep, 893 all over our period of 1.14 all over 2 pi, and that is all squared. And so this gives us a spring constant of 27,126, and that is the same as 2.71 times 10 to the 4 newtons per meter. There we go. John wonders whether the car body is moving in simple harmonic motion. State the conditions for simple harmonic motion. Alright, so this is the classic question that's in every exam. In order for the system to be in simple harmonic motion, there must be a restoring force that is proportional and in opposite direction to the displacement. And you can write that in. John has a mass of 103 kgs, and while he sat on the roof, his weight is supported by each of the 4 wheels equally. Determine the initial amplitude of the oscillation and hence the maximum acceleration of the car as it oscillates. So we know that F is equal to kx. Now the marking schedule says F is equal to ky. Don't worry, that's the exact same thing. It's just using y because we're in the vertical direction, okay? So F is equal to kx. So x is equal to F all over k. We found our spring constant in the first question right here. And our force is the weight force of John. Now be careful, it is not the weight force of the entire system, right? It's not the weight force of John and the car. The reason for it is because if we have a car here, okay, car on wheels, when the car is on wheels, the suspension system has already been compressed a given distance. And that distance is now its equilibrium position. It's just going to rest there, okay? However, if we add another mass onto the car, in this case, this is going to be John, okay, now the suspension system has to carry more weight, and so it's going to compress even more. And so if we're trying to calculate the amplitude, we only want to take into consideration the extra weight on the car, okay? And our spring constant was given as 2.71 times 10 to the 4, okay? And this gives a displacement of 0.0373, okay? And that's meters. There we go. All right. Now we know our acceleration is equal to omega squared y. Now, in our formula sheet, it would have a negative there, but again, that's just the definition of simple harmonic motion, where our acceleration is in opposite direction to our displacement, okay? But in this case, we really only care about the magnitude, so we don't have to worry about that. So we found our y value, which was our x value, so I should probably replace that as x right there, okay? But we don't have our omega. But what we do have is the period given up here. And we know that our omega is equal to 2 pi all over t, and so our omega is going to be 2 pi all over 1.14, okay? And so we can plug that into here, and we get our acceleration is equal to 2 pi all over 1.14 squared times our x value, which was 0.0373, and this gives an acceleration of 1.13 meters per second per second. There we go. John and his friend Rick ride in the car together. Speed bumps in the road are 10.5 meters apart when they are traveling at 8.33 meters per second. The car builds up very large oscillations. Explain why this happens and determine Rick's mass. Okay, so this phenomenon is called resonance, and this is when energy is added into a simple harmonic motion system at its natural frequency. And so as energy is added at its natural frequency, the oscillations build larger and larger. So you can write that part in first. So we are given the distance between each speed bump, and we're given the velocity that we're traveling at. Velocity is distance over time, and so therefore time is distance all over our velocity. And in this case, this is the time in between each speed bump, and so that is our period. So our period is distance all over our velocity, where our distance is 10.5 and our velocity is 8.33. And this gives a period of 1.26 seconds. There we go. Right, so now that we know the period, and we also still know the spring constant of the springs in the car's suspension system, we can use this equation once more. All right, this equation. And we can rearrange for mass. Because we know the mass of John, and we also know the mass of the car, when we rearrange for mass, we can simply take the mass minus John's mass and minus the mass of the car, and we'll be left with Rick's mass, okay? So that's what we're going to do now. So now, rearranging for mass, we again get t all over 2 pi, and that's equal to square root m all over k. T all over 2 pi squared is equal to M all over K. And so therefore T all over 2 pi squared times K is equal to our mass. And so 1.26 all over 2 pi squared times 2.71 times 10 to the 4 is equal to our mass, okay? And this gives a total mass of 1,089 kgs, okay? So that is our M total, 1,089 kgs. So therefore, 1,089 kgs is equal to John's mass, which I'm pretty sure is 103 kgs. Yep, 103 kgs. So 103 kgs plus the mass of the car, which is 893, plus the mass of Rick. And so 1089 minus 103 minus 893 is equal to the mass of Rick. And this means Rick's mass is 93.8 kgs. There we go. And this 0.8, by the way, came from the fact that I used the whole value of this value right here, okay? Just to clear that up. And with that, we are done. See you.